Paige Boyd, and we're in the Senior Design Group for Environmental Engineering at San Diego State University. I'm going to be talking about the breakthrough curve in this experiment.
My name is Ivan Ruiz, and I'll be talking about the characteristics of activated carbon.
I'm David Coven. I'll talk to you about hydraulics, head loss, and upflow versus downflow in our column.
And I'm Sean Sudol, and I will run through a brief design description for you. One of our biggest design challenges was locating and acquiring materials to meet our calculated design specifications. Construction took ingenuity and countless hours tracking down parts and materials in order to properly treat the contaminant solution as specified in our design. Enjoy this video. It's Sean Sudol, and I'd like to run through a brief design description of our activated carbon treatment system. Here we have the tubing, which will go into the contaminant reservoir. The contaminant reservoir will contain 5 milligrams per liter solution of methylene blue, which we'll consider our contaminant for removal. The tubing will then run through our 1/2 horsepower peristaltic pump from Masterflex. The pump will be running at approximately 1.14 gallons per minute once it goes through our treatment system. From the pump, our inlet is a 1/2 inch, 12-inch section of PVC, which immediately runs in to a 90-degree elbow. The 90-degree elbow sends the influent up into a 3.5 section of 1-inch PVC into a 1-inch removable ball valve. The ball valves will be used in the case that we needed to remove a column for treatment or maintenance. They would screw off at the bottom here and the top here, and the entire column would be able to be removed from the system. From the ball valve, we have another 3.5-inch section of 1-inch PVC going into a 1 to 2 expander. The 1 to 2 expander goes into a 2-inch to 3.5-inch expander cap, which then connects to our column here. The column is a 3-foot acrylic column, outer diameter 3.5 inches, inner diameter 3.375 inches. The bed height is approximately 2 feet 9 inches. At the bottom of the cap, we have a circular piece of steel mesh. On top of that, we have glass wool, and on top of that, about a 1/2-inch section of glass beads. And this is in order to keep all of the activated carbon within the column and not have it leave with the effluent. So after the 3-foot column, there's another section of glass wool, glass beads, and steel mesh into a 3.5 to 2 reducer, a 2 to 1 reducer, a 3.5-inch piece of 1-inch PVC, and another ball valve, removable ball valve. The system then goes into the second set. We have another 90-degree elbow connector here, a 5-inch piece of 1-inch PVC, and then another 90-degree elbow sending the contaminant water back down. After this 5-foot section piece of pipe, we have a ball valve here, which can be closed in the instance that we needed to remove the second column. In order to prevent water or leakage from exiting the system, we would shut this down so water from our center column or our center connecting pipe would not leave the system. From there on, we have another 90-90 connection here with elbows running back into another ball valve, into another 3.5-inch piece of PVC pipe going into the 1 to 2-inch expander, and then the 2 to 3.5-inch expander cap running into exactly the same series that we have here. The first and second column setup are identical. So after that, we have the 3.5 to 2-inch reducer, the 2-inch to 1-inch reducer fitting into that, and then into another PVC ball valve PVC fitting. The effluent will then leave through this elbow into another 1.5-inch, 1-foot section of PVC, and then we'll come through this tubing here into our clear well, which will be located at ground level, the same height as the reservoir. And that is the design description.
Okay, in order to determine the size of the pilot scale, which will be used in our presentation, we have to first determine a breakthrough curve. To determine the breakthrough curve, we used a small column which we filled with activated carbon. We had glass beads at the bottom to make sure that no activated carbon came out, and glass wool to make sure that none went through the tubing. We connected the tubing to the column through a Masterflex peristaltic pump, which basically forces water into the tubing and out through the column. The first step of this experiment was to determine the flow rate, which we found it to be 0.47 liters per minute, so roughly 0.5 liters per minute. But this did not sufficiently treat the water, which with methylene blue, 5 milligrams of methylene blue. So we next used a larger column, which we filled all the way to the top with the same apparatus with the glass wool and the glass beads at the bottom. This we used at 0.47 liters per minute as well, and we determined the breakthrough point, which is 5% of the influent concentration, and then as well as the exhaustion point, which is 95% of the influent concentration. To determine the breakthrough curve, we tested the effluent concentration every couple minutes and placed this into a cuvee, which we tested in a spectrophotometer, which gave us an absorbance reading that we could test to get or plot on the calibration curve and determine what that concentration was.
As you can see, we've designed our system to run in series. That is, one column will follow the other. We have done this not in parallel to allow for a full exhaustion of the carbon before it needs to be replaced. If there is only one and they're run in parallel with the flow is split evenly, they can only be run to absorbance of each column and then they would have to be replaced. But this allows for further treatment before regeneration of the column is required. It also is an upflow system. Many systems run downwards to take advantage of gravity, but we thought that an upflow pressure system would be a better fit for our design. Upflow allows for even flow up through the column, where there will be less channeling throughout the system, as it could be in gravity. Allows for an increased contact time over downflow. Downflow is often used as a filter as well as treatment. We don't have any suspended particles in our effluent concentration, so we will just have an upflow, and it won't require any backwashing throughout the system because it will not clog the pores. Instead of having the time to just fall through with gravity, we will slowly rise the controlled flow rate to have an even contact time and we will evenly treat and evenly exhaust the carbon. Water will enter the system at the bottom from our peristaltic pump. Once it enters, it will immediately start undergoing head loss. Head loss will be done through the pipes, through the elbows, through the expansions and contractions, and through the bed itself. There will also be head loss due to the change in elevation from where it enters and leaves the system. That will be about 5 feet of head, and that'll be the bulk of our head loss. The other head loss through the pipes and through the bed itself and contractions and expansions are minimal in comparison. The total head loss of the system comes out to 5.2 feet of water.
Granular activated carbon is commonly used for removing organic constituents and residual disinfectants in water supplies. This not only improves taste and minimizes health hazards, it protects other water treatment units such as reverse osmosis membranes and ion exchange resins from possible damage due to oxidation or organic fouling. Activated carbon is a favored water treatment technique because of its multifunctional nature and the fact that it adds nothing detrimental to the treated water. Most activated carbon are made from raw materials such as nutshells, wood, coal, and petroleum. Typical surface area for activated carbon is approximately 1,000 square meters per gram. However, different raw materials produce different types of activated carbon varying in hardness, density, pore, and particle sizes, surface areas, extractables, ash, and pH. These differences in properties make certain carbon preferable over others in different applications. The two principal mechanisms by which activated carbon removes contaminants from water are adsorption and catalytic reduction. Organics are removed by adsorption and residual disinfectants are removed by catalytic reduction. Factors that affect the performance of activated carbon are molecular weight. As the molecular weight increases, the activated carbon adsorbs more effectively because the molecules are less soluble in water. However, the pore structure of the carbon must be large enough to allow the molecules to migrate within. A mixture of high and low molecular weight molecules should be designed for the removal of the more difficult species. Particle size. Activated carbon is commonly available in 8x30 mesh, 12x40 mesh, and 20x50 mesh. The finer mesh gives the best contact and better removal, but at the expense of higher pressure drop. A rule of thumb here is that the 8x30 mesh gives 2 to 3 times better removal than the 12x40, and 10 to 20 times better kinetic removal than the 8x30 mesh. Flow rate. Generally, the lower the flow rate, the more time the contaminant will have to diffuse into a pore and be adsorbed. Adsorption by activated carbon is almost always improved by a longer contact time. Again, in general terms, a carbon bed of 20 by 50 mesh can be run at twice the flow rate of a bed of 12 by 40 mesh, and a carbon bed of 12 by 40 mesh can be run at twice the flow rate of a bed of 8 by 30 mesh. Whenever considering higher flow rates with finer mesh carbons, watch for an increased pressure drop. Activated carbon's adsorptive properties are used to remove organics. Generally, adsorption takes place because all molecules exert forces to adhere to each other. Activated carbon adsorbs organic material because the attractive forces between the carbon surface, which is nonpolar, and the contaminant, which is also nonpolar, are stronger than the forces keeping the contaminant dissolved in water, which is polar. Activated carbon can remove and destroy residual disinfectants, chlorine and chloramine, through a catalytic reduction reaction. This is a chemical reaction that involves the transfer of electrons from the activated carbon surface to the residual disinfectant. In other words, activated carbon acts as a reducing agent.
Completely blue water enters, 5 milligrams per liter, goes through 2 columns, sufficiently treated to perfectly clean, potable water.